Um, Today we're going to be looking at something called a production function. Okay, so what is a production function? A production function is essentially just a function we have that is used to work out output. Okay, so we have a bunch of physical inputs here in some sort of function which we use to work out output. These physical inputs are just factors of production. So they could be labor, capital, land, and so and so. And we can have infinite many inputs, but usually the inputs we use are labor and capital, L and K. Okay, so let's look at a very simple production function. Here we have Y, which is output, is equal to labor plus capital. Okay, output, labor, capital. Okay, so what does this mean? So output is just how much is produced. Labor is number of working hours done by humans in a specified time, and capital is the value of all all things used to aid production, or should I say physical things. Used to aid production, such as roads, buildings, tools, etc., etc. Okay, but what does all of this actually mean? So let's say we have 4 units of labor and we have 5 units of capital. In this model, what we will get is 9 units of output. So that's essentially what it is. We measure our input, our physical inputs, and we get an output. So how much is produced. This is very simplified model. But we have loads of different models, such as Cobb-Douglas model, Leontief, SES model, constant elasticity of substitution, which is just a simplified version of Cobb-Douglas function. Okay. So why do we use production functions? We just use them so we can analyze them, so we can find out the most useful and the most efficient inputs, the most efficient inputs we can put in. Basically, we can find the combinations and permutations of our inputs. So in this model, there is no really optimum. There is an optimum, but it's based on price. Okay. So capital and labor have the same value essentially on output. So if labor was cheaper, we'd just spend all our resources on labor and none on capital if it was cheaper, and we'd get 100 units of output. Obviously that isn't realistic, but that's essentially what we're doing when we make these models. We're trying to find the optimum combination of inputs to produce outputs at the lowest cost. Okay, let's look at this on a graph. Okay, so here we have a univariate production function, okay, where our input is just labor and we get an output. So if we put, let's say this is 10 units of labor in, we will get 10 units of output. Just made up those numbers. It could be 5 and 10. That's it. Okay. So this is just a function that's made up. It looks something like this. Okay. So this function can be split up into marginal product and average product. So what marginal product is for every extra unit of labor, how many extra units of output is there. And we get this by simply taking a tangent of the line, differentiating it. So at that point, what is the rate of change of output with respect to labor? Okay, and if we graph this on another graph, which is down here, the same graph, but we've included marginal product and average product, we will get a graph that looks like this. So what it is here, our gradient is increasing, but at a decreasing rate. So as you can see here, our gradient's increasing. Okay? But once we get to this point, the point of inflection, our gradient starts to decrease. I know it's not exactly the right point, but our gradient starts to decrease. And that's what's happening here. Our gradient is decreasing. So for past this point, for every extra unit of labor, we are getting less output than the previous. Okay, average product now. Average product. So here it would be our total product divided by the quantity of labor, not the quantity of output. Okay, so what is our output here? So what is our product here? Output. And what is our labor? So let's say that's 10 and that's 5. It would be 10. We get 10 output for 5 units of labor. So each labor produces 2 units of output, which is our average product. Okay? So here we can see that our average product is increasing because as we go along, as our labor increases, because for each unit of output we're getting more units of labor than our average product, until that occurs up till this point. And at this point, each extra unit of labor produces less output than the average. So that's going to start dragging down our average product. And therefore, at this point, our average product starts to decrease down like that. And that is only when our marginal product goes below the average product. That's pretty much it. Then let's look at this. Let's look at how to prove this graph. How to prove what's going on down here. And that's how we do that is we differentiate our average product. So our average product, let's redo this. Our average product is equal to our average product is equal to our total product over quantity of labor. So if we differentiate our average product with respect to Q, quantity of labor, so to differentiate this, we will have to use a quotient rule. Okay, so first of all, we have to differentiate total product and multiply it by Q. So total product differentiated is MP. As we looked at before, when we differentiated this graph, we get the gradient, which is the rate of change of labor, which is the rate of change of output with respect to labor, which is just marginal product. Okay, so it's marginal product minus total product times the differential of Q, which is just 1, over Q squared. Now let's further simplify this. Q MP minus total product, which by rearranging this graph, by rearranging this equation, we get Q times by AP equals TP. Q times by AP equals TP over Q squared. Okay. Here we can just take out a Q from there, a Q from there, and a Q from there. So we get MP minus AP over Q is the differential of average product with respect to Q. This essentially just proves what we've just said in this graph. So let's copy this over. Okay, so when our marginal product is greater than our average product, we have an increasing function. Our average product is increasing, as you can see here. But as soon as our marginal product is smaller than our average product, our function starts to decrease. So that's exactly what this graph is saying. We can prove it like that. Okay. So the issues with the production function is there's lots of different issues, but one major issue which came to the light around the 50s is that it was an argument between MIT and Cambridge, and it was regarding the idea of capital. Capital, unlike things like labor, other physical inputs like labor, land, is very difficult to quantify, and this makes production functions a bit, let's say, iffy, if you get what I mean, because they are so difficult to measure. And because of this difficulty, people argue that production functions don't really mean anything, because the capital, when we put most production functions involve capital. We'll go over lots of production functions in the future, but capital is just so hard to measure, so it makes production functions redundant. They're not useful, and that's the major concern. But despite all the many problems with it, people still use it because of it's very easy to algebraically manipulate. They are very easy to algebraically manipulate, as we just saw when we took the marginal product and average product. And they're also just simple. And that's why people still use them to this day, even though they were made around the 1900s. That's pretty much it. That's just an introduction of what we'll need. Next time, I'm just going to actually look at production functions. I'll actually look at specific production functions. So next video will probably be Cobb-Douglas production function. That's about it. Thank you for watching.